So, let us say what we were doing. I mean, at least in my part, we were explicitly focusing on infinite population, homogeneously mixed and all that, where everybody is talking with everybody. And then you have this concept of ESS propping up. We saw a few important things about ESS. The main theorem which we were after was that ESS is asymptotically stable fixed point. And while trying to prove that, we sort of saw that evolutionary game theory is lying at the overlapping region of game theory, information theory and nonlinear dynamics, at least from the perspective of infinite population. And then we sort of applied this to a quote unquote real life problem of evolution of cooperation using a toy model. Now, one can make it more and more difficult, and you can read lots of research papers on how in various ways evolution of cooperation happens. And then we saw a natural setup where you can end up getting pure strategies in continuum form, right? Which was, if we go to reactive strategy space, we have the probability of cooperating if my opponent has cooperated and probability of cooperating if my opponent has defected, and this probability can range from 0 to 1. Hence, I have continuum of strategies possible with me. Now, once your strategy space becomes continuous, the pure strategy space becomes continuous, the theorem which we prove now need not be valid. Very easily you can think about it, because when we prove the theorem, we wrote replicator equation. If you think about replicator equation, we had terms like x1, x2, x3, x4. They were countably many, right. So, anyway the framework was with finite number of traits, and on top of it, and basically this percolated through all that, and whatever we wrote about the scale divergence, that was also written for discrete probabilities, right. It was written for a PMF, not for a PDF. And really for continuous strategy space, I do not know how to write down the replicator in simple form. I have to go to some integral forms and all that. So, there is no guarantee that if I have pure strategy space which is continuous, I am going to have ESS to be asymptotically stable state. So, it could be ESS exists, but you do not even reach there. Okay. So, this happens even in the cases where replicator equation is not important, some other equation is important. But we come to this setting naturally, and then we ask this question to begin with. What we did in replicator equation actually was this: you had a population, and then one of the let us say mutant came up, and then after some time there were 3 of them, and then at some point all were dark. Then maybe what happened was, next step is you have all dark, and then suddenly a blue circle comes up. The next step would be this blue circle sort of may have taken over some of them, and then everybody is again sort of I did something wrong. So, this blue, yes, fine. So, this blue circle throughout. This is usually how evolution sort of would go on, the way we discussed it. So, the part here that you came from here to, let us say here, is essentially what you cover under replicator equation, where what is happening is you have replication, and the after replication the one who was fit got selected. So, this was a replication selection process which was going on. How this mutant came up we never discussed. We said somehow the mutant is there. Once the mutant is there, this happens. Now, from this step onwards, or rather after this, when mutant came up, then we can ask the same question once again, and then from here to here the dynamics will again be governed by replicator equation. This is again a replication selection process, and this keeps on going. But what if I see this, and hence what we are talking about is microevolution at every step. I mean of these 6 steps, this is where microevolution has happened, this is where a microevolution has happened, because the frequency of the particular traits are getting changed. Here it was what 4 by 5 versus 1 by 5, which now became 5 by 5 and 0 by 5. Okay. Now suppose my question is something else. My question is, it started somewhere. So it started sort of here, where let us say you had all circles. Now I want to know from here, I see this flash, then I see this as a flash. Okay. So what we are now talking about is this, this, and then this. Let us say this is what I am seeing, that there was a population, a mutant came up, and suddenly the population now looks like this. Mutant came up, now the population looks like this. And this is how sort of evolution is happening. This is a long term evolution. This evolution which we have written here is in a way bigger than this microevolution, and it is a long term evolution that we are looking at. And this definitely is mutation selection process. When now what you are saying is a mutant comes, it gets selected, another mutant comes, gets selected. You are not talking of any replication explicitly. There is a black box inside how you went from here to here. That black box is controlled by replication selection, but otherwise I am interested from here to here to here. So now your variable of interest is not frequency anymore. Your variable of interest is the value of the trait itself. You want to know how a trait changed from this to this onto that. Yes.
Is this just not coarse graining the entire process?
Yeah, I mean, you are reducing my 15 minutes talk to 2 words. Of course, that is what it is in a way. True. But it's a coarse graining more in the sense of time, that you are basically saying I don't care, I just take blips. Okay. It is not actually coarse graining in terms of averaging things out and doing mean field theory. Replicator also was mean field. I could have derived replicator starting from what Supratim is doing for you, starting from Moran process, and then from Moran process I can go to a thermodynamic limit where I can get replicator equation. Okay. But that is not what we are doing. It is always, so it is coarse graining in the sense of time, if you want to say that. You do not just look at these things. Fine. So I am going to use coordinate x. Do not confuse yourself, nothing to do with earlier lectures, because this is sort of very common in the literature. I think so. This is the book Darcole and Rinaldi, evolutionary, something like analysis of evolutionary processes, something like that. The title might be a little wrong, but if you Google, you will find only one book with those 2 authors, but it is along that line. So in that book, you will find more details about all these things and how sort of the historical context, comparative studies between various takes on this matter and all that. Okay. We do not get into this, otherwise we will not be able to finish anything. And what they essentially talk about is something known as adaptive dynamics. That is what we are interested in, because what we are saying is mutation has come up, it has got adapted to the environment, then the mutation has come up and has got adapted to the environment. So some kind of adaptation is happening at every step. So now I have to write down an equation for how trait is evolving. I cannot write down replicator selection, I have to write something else. Now again, that equation which we are going to write can also be derived from microscopics and all that. It is going to be, I mean, a long derivation you can find in that paper. We are just going to write it more phenomenological way. Okay. If you are interested in derivations, you can sort of look at that. So, first thing, trait values will be denoted by x. So, let us say height, if that is the trait, it can take continuous values. Okay. And in our example of direct reciprocity or repeated games, the trait value would be a vector, because you have two quantities specifying a trait, p and q. So, trait value can be vector, trait value can be scalar. Okay. You may require more than one parameters to define a trait. For simplicity again, because it is just going to make things complicated, concepts will be hard to sort of convey to you. We will just stick with trait values where only one parameter is enough or one variable is enough.
What do you mean by two parameters?
P and Q. So, think about suppose I am a reactive strategy guy. So, strategy is a trait, but to specify my strategy you have to specify two things, P and Q. Remember what P was? P was probability of cooperating when the opponent cooperated, and Q was probability of cooperating when opponent defected. Unless I specify both of them, you have not specified my strategy, and hence you require two parameters or variables to specify my trait. So, to specify one trait you may require more than one parameters. Here I am a bit being loose, but because you have done nonlinear dynamics, you have to be a bit careful, since this has the flavor of nonlinear dynamics. Usually when we talk about variables, we mean something whose time evolution we are seeing, and when we talk about parameters, we mean something which has been fixed right from the beginning. Parameters can be time dependent as well, but then right from the beginning what that is. Okay. But here sort of I am using those words a bit synonymously, but you have to be careful from the nonlinear dynamics perspective. So, to be very precise, I would say these are the variables, because I am going to write down equations in terms of them. Okay. But if you just think in terms of game theory, then to specify the trait you require two parameters. Okay. So, there is a clash of jargons. Okay. So, just be careful about it. Is that clear that trait can have multi parameters? Okay. And this can change continuously, it can take continuous values. I mean such a scenario, we have seen an example of that already. So, I want to write down an equation for this, that how it is going to evolve or change or whatever. So, how to write that down? So, of course, okay. Even before that, the crucial ingredient in this theory, this adaptive dynamics theory, is something called inversion exponent, or sometimes known as inversion fitness as well. The notation we are going to work with Sxy. What does this mean? Sxy is per capita growth rate of y trait in X traded resident. This is the most crucial ingredient in adaptive dynamics. So, what you are saying is, if there is a population of these white circles, if you get a solid circle which is a mutant, how fast this is going to grow is going to depend on, I mean it is going to depend on definitely what trait is already present. So, the growth rate of this may be different from growth rate of this in this resident. It might change as your residents change, hence that X dependence is there. So, that is from the perspective of mutant, that is not fitness from the perspective of resident. If I were to talk about from the perspective of resident, I should have been looking for the term this, because now you are talking about a resident in the population of resident. So, here we make an assumption that we are already at demographic attractor. Specifically, we just work with the fixed point for the time being. What do I mean by that? Because that is all about growth rate, so things can keep on growing all the time. It serves two purposes. One, that it talks about how traits are going to change, but by definition it is a growth rate. So, when you wrote down logistic equation or you talked about Malthusian growth and all that, it is also talking about how the entire population is going to grow. Okay. But then you know the entire population at some point of time is going to settle down somewhere at some fixed point and it is not going to change anymore. So, I am going to take that out of the context because I do not want to focus right now on the ecological part, I am focusing more on the evolutionary part. So, I am assuming that we are at the demographic attractor, which means population is fixed, which means if growth rate of x in population of x should be 0. So, this follows from our assumption that we are at demographic, or rather than assumption, this is a construction which you are doing. If by construction Sxx is 0, population is fixed, not changing at all, only traits can change. Okay. Fine, any questions up to here? So, in the context of, so how are you going to find this? Of course, experimentally and all that, and people will write different functional forms depending on how things are there. I mean, in principle, this should depend on the size of the population as well, which we have taken out because we have assumed this, because that no longer matters. Yeah, so I was just coming to that, yes. So, how to calculate invasion exponent? The invasion exponent, if let us say there is game going on, then it can also come from the payoffs. Okay. For example, when we talked about payoffs in the last case, we can write something like payoff of u strategy 1 PQ strategy PQ minus strategy PQ strategy PQ. Okay. What I have written here is, I have gone to the notation of reactive strategy space, and in that particular example, if I want to find out how much a mutant P prime Q prime, because now you have two parameters to define a trait. So, how would you define a strategy which is let us say somewhere in this reactive strategy space which we were drawing, that P versus Q. So, there is some strategy there that has to be defined by two of them. I am just writing S to say that this is a strategy. Now, this strategy can compete with some other strategy which is let us say resident for the time being, and that is this strategy. This is the resident. So, this is the coordinate P Q and this is P prime Q prime sort of. So, when this appears, it is going to compete against this and going to get some payoff, but this was already getting payoff against itself, which is this. If you subtract this, you can see trivially, if I put P prime and Q prime equal to P Q, it becomes 0, which basically means Sxx equal to 0. Otherwise, it will give you something which can be positive or negative. If this is positive, then you expect P prime Q prime to grow. If it is negative, you expect P prime to go down. So, theoretically, when you are doing two-player games and all this game theoretic stuff, then the way to calculate this is something like that. Okay. Otherwise, realistically, you have to come up with how exactly the Sxy depends on, that has to come from your experimental data and all that. So, that book sort of will help you if you want to have a look at it. I will come to that. No, so there will be ESS. It is not about, so I will just come to that. There will be ESS, the only problem will be ESS may not be asymptotically stable. It is the ESS in a way, it is a local thing. But that is a very important point, it will require some build up. But any questions up to here? This is actually the Haber-Sigmund's ESS definition kind of a thing, the third definition. It is basically saying if fitness is high, you go up there. So, you try to reach the ESS, that is what it says. But will you really reach the ESS all the time? That is the question. In replicator we showed you will, but here we will see you may not. And the mathematical catch is P and Q are now continuous. You cannot write down replicator equation, at least in the form we wrote.
Is U the same thing as?
Yeah, U is the payoff.
Sir, can you explain that notation?
U P Q 1? Okay. So, that will mean we will sort of revise this a bit. So, what we are saying is, if you remember, we had the P Q space, I take a point P Q prime and a nearby point P Q. What was the question we were asking in the repeated game? Remember, we were trying to create matrices like this, where I had strategy S1, S2, strategy S1, S2, and we were filling things in. Now, this together forms a strategy, this tags the strategy. So, I am calling this what I have called that S1 or S2, or I have just called it S. So, this is let us say S1 and I am denoting it as function of PQ, and similarly this is S, which is denoting as S2. So, then this is nothing but S PQ and this is S P prime Q prime. Now, I want to know what do I put here, right. So, what do I put here? This will be U and the strategy is S1, S1, which will be S1 is this, S2 is this. It is exactly same thing.
So S is the inversion expression.
That is capital S. I am safe. No, is that capital enough? Oh, that is the, I now understand what is the problem. So, this let us put bar, 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 bar.
So this is for strategy.
This is just stands for strategy. Yeah, I thought I can differentiate between capital and, but I do not differentiate between small guys, big guys. Okay, if that was the confusion, now it's clear. Okay. So, now this is the crucial ingredient I want to. Now, what is it a mutant is going to do? Let us think a bit of geometrically. You essentially have, from the mutant perspective, at a given x, you see everything is from mutation perspective. So, where you are is called mutation limited domain. So, mutant is going to see some landscape of this fitness, and then if mutant is here, let us say, it would want to go up because that is where the fitness increases, and then once it goes there, it would not want to come down. So, it sort of goes and settles down at the local maxima. If there is a local maxima here, then it goes up and settles down here, does not want to come down, but there already was a higher maxima. That does not matter. I mean, that is why evolution does not optimize things to the maximum possible, the best possible optimization, but it optimizes locally, that you cannot deny. Okay. But here comes the bigger problem, which is this thing also depends on x. So, once y has fixed somewhere, y has changed to some point, then this graph is no longer like this, it can be something else because it was x dependent. So, at every time this fitness landscape is going up and down and changing the way it wants depending on how the x has changed, because the y of previous step is x of the next step, and since x has changed, the new y which you can call y prime will see a different sxy. So, this landscape is changing. So, it is called adaptive fitness landscape. Fine, questions? Yeah.
So when we say y in this step is x of the next step,
Yes.
are we assuming the all fitness is mod for x, all y will become x in the next step?
Yeah, if only that. Otherwise, no. Otherwise, it will remain fixed in the next generation. Yes, true. So, either it will remain fixed or it will change, but it can change. Yes, please. Inversion exponent itself with respect to y coordinate, and hence the word adaptive. Otherwise, the fitness landscape we always know. I mean, there is the standard stuff in genetics and all that. Fine. So, now we write down the equation phenomenologically. This equation is called canonical equation of adaptive dynamics. So, basically we are still doing evolutionary game theory because S can come from games as well. Okay. So, first assumption, or rather let us call it what we want is, we want to write canonical equation of adaptive dynamics. We assume mutation is small. That means, in my abstract space of traits, you can think of the TQ space all the time as an illustration. If resident is at a point 0.5, 0.5, then my mutation is going to be in the neighborhood of 0.5, 0.5 only. Mutation just does not appear. So, if I am ALDI, always defect strategy, I do not consider tit for tat to be a mutant in this formalism, because tit for tat is far away from ALDI. Remember, ALDI was on the baseline and they were far away. So, I am assuming that the mutants are going to come only close to the resident strategy. This thing can be relaxed and something else can be done, but that would not be adaptive dynamics, I mean in the deterministic sense. So, that is an assumption, and that is sort of biologically relevant. Usually mutations are very small, slow mutations around whatever is happening, or at least you can say like that, only when those things are happening, there I can apply this, does not matter. Second is, mutation is rare. This means what? Remember, we had the process going on, and during that process of fixating from one trait to other trait to other trait, we did not assume during the process of replication selection another mutant came up. So, we want only one mutant to appear very rarely, it goes and substitutes the resident, then the next one comes, substitutes the resident, then the next one comes, in between no other mutants come. This can be assured by just claiming that mutants are very rare. So, that is another assumption. The third assumption which is driving the equation is sort of invasion implies substitution. You see, it has become a black box. We say mutant comes, mutants take over. When mutant comes, we say mutant is invading the population if mutant's fitness is more than the resident's fitness, and then we say mutant has taken over the population. It is a blip. We are not sort of, in one blip you are there. You are not thinking of what is going on inside. So, you assume that as soon as invasion has started, invariably substitution of the resident is going to happen. Okay, it is an assumption. So, that is the third assumption. There is no coexistence here. Up to coexistence can come, but within the paradigm of this equation only. Okay. Fine, makes sense. Okay. So, now let us write down the equation. So, equation is your change of trait value should be proportional to how the fitness is changing, the rate of change of fitness from the perspective of the mutant, that is the rate of change of fitness from the perspective of mutant. That is why I am doing partial derivative of the invasion coefficient with respect to y and not x. But where should I do it? At y equal to x. So, I am the resident. At that resident, I mean in this abstract space of traits, there is a point where x is. At that point, there is a direction in which S is changing fastest. From the perspective of mutant, I want to find out the fastest rate of change of this invasion coefficient at this point, because the velocity is at this point, velocity in terms of y. So, that is what you are writing at y equal to x. See if it works for you. This is the fastest rate of change that mutant would see given the value of S at that point.
So like S can be thought of as a field of some sort.
Yes, it is a scalar field.
That is driving the.
Yes, just like non-linear dynamics stuff. In the non-linear dynamics, when you did the equations, your vector fields were derivative, the x dot and y dot, they were derivative with respect to time. And you were saying with respect to time, so what was when you were talking about x dot equal to fxy and y dot equal to gxy, what are you saying? You are saying I have a space of xy, I have a field of velocities. At every point the velocity is given by x dot comma y dot, which is explicitly written as f comma g, and that tells me how things are going to move in the next step. It is exactly like that. Now, instead of t driving it, you are saying how x, I mean the y drives it.
So how is x dot proportional to?
Oh, because of the fact that you are assuming the third assumption, that once x is that of the resident, you are asking in this step resident was x, in the next step what is going to be the resident? So, the resident is going to be whoever was the mutant here who had higher payoff or higher invasion exponent.
So like minus होगा.
Q minus होगा. X नहीं घटेगा, X Y बढ़ जाएगा. There is nothing like X reducing, Y decreasing or anything like that. X and Y are all same. You are explicitly looking at the tags for what is mutant, what is resident. If this Y, if this goes from this point to a point where it is Y, in the next step, X has become the Y. So, value of X has changed, it has nothing to do with X ka ghatna badna, X has been substituted by Y. So, all you are saying is the rate of change of invasion exponent, if it is positive for the mutant, x will be driven that way, otherwise it won't be driven that way. It is the gradient essentially, it is the fastest change. This proportionality constant, now that requires precise derivations. This proportionality constant can be removed to put some x dependent stuff which depends on mutation, how mutation happens, what is the covariance of mutation, this, that, etc. Many things can come in here, okay. But it is usually positive, not usually, it is positive. So, what one can do is one can absorb this in time, and one ends up writing in a very simplified form in the case you have only one variable for specifying trait as just this. And that is your canonical equation for adaptive dynamics in 1D. Okay. So, now we have to analyze this and we have to get to some interesting result. The most interesting result that we are after, it has the capability of showing speciation, that two different traits can come up and coexist together. Okay. So, let us say that is what we want to understand, but to reach there we have to do some of the mathematical jugglery. Yeah.
Can you relate that with the graph ones, this landscape that we have?
This one?
Yeah, and the graph that we have, S and Y.
S and Y. I mean, it's by S and Y it's simple in the sense that if Sxy is changing with respect to y and Sxy is okay. So, if this is more, so this definitely is more than this. So, that means if I take the derivative of this with respect to y, this is a positive thing. So, I am going to move towards this. Earlier my residence was x here, now the resident will become x here. So, x has increased in that sense.
So, X is the average value of the trait?
Nothing average value. X is the trait value.
Okay, so we are assuming that here, it's invading completely.
Yes.
Instantly.
In the time scale we are talking about, it instantaneous. Within that instant, full replicator has happened in a way. Yeah.
Explain how you basically
Oh, how this has been removed?
Yeah.
Oh, just by saying, this is ddt, I can take this kx inside here, but of course I have to do some integral stuff because there is x and all that. But usually there is a standard thing that if this thing, in general, if I have a nonlinear equation with a positive definite matrix in front of it, that can always be absorbed in time and time can be made nonlinear, topologically results do not change. So, anything which is positive definite never changes anything, you can always absorb in time and redefine time. Okay. So, we just say okay, I mean think of it as a constant, then we can just multiply this t with the constant. Yeah, then it will decrease. This derivative can be negative, not this.
Yeah, so but does it make sense for it to change even if this S actually decreasing or to change?
Basically, you are coming back from the mutant perspective. You are basically saying you are coming back. That's all. Because it's everything from mutant perspective. The resident takes you back. Fine.
Coexistence here means the slope will be 0 at some point.
Yeah.
So the x is
Yes, exactly. So exactly that's what we are going to do now. So let's go ahead. I luckily have 30 more minutes. I mean, not during coffee, of course. 30 more minutes off Supratim's life. I'll return it back. I have more diseases than he. Canonical. Okay. So now let's start with x dot equal to del s xy del y y equal to x. Let us do simple fixed point analysis. It is a very simple thing, it is a 1D equation. You have done much harder equations when Shitabro did for you, right. The only place where it becomes a bit messy for beginners like me and you is that when we take this partial derivatives, there is sort of mess. Okay. So, one has to keep track of which one is kept constant, which derivative has been taken and all that, otherwise it is very simple. Let us call for this as x to very sort of explicitly impress upon you that ultimately you take the derivative and then you put y equal to x, this entire thing is only function of x, there is no y remaining there. Okay. So, now you can explicitly see that this is nothing but a one dimensional ordinary differential equation. Things cannot get easier than this. Okay. So, now what do we do? Whenever you have a nonlinear differential equation, you know you cannot solve nonlinear differential equations in general, because there exists no theory which helps you to do that. So, you say okay, let us try to look for certain solutions which are easy to solve. The easy solutions are to find fixed points, because to find fixed points I do not have to solve the equation, I can just solve the equation algebraically, right. So, what would be a fixed point? So, fixed point would be whenever a of x at x star equal to 0 will tell you that x star is a fixed point. A fixed point in CAD, adaptive dynamics, is called evolutionary singularity or a singular point. These are just jargon. Now, if this evolutionary singularity has to be stable, what do I have to do? What is the condition? It is a 1D differential equation, this and this given. What is the condition? The derivative of a less than 1, greater than 1, less than 0, greater than 0, less than 0. So, if this happens, your x star is convergent stable. That is the jargon in adaptive dynamics literature. So, let us find out the condition and at least for once see that how this looks like. We do this thing. What I am trying to say is I have to express this in terms of this. Okay. So, d dt of del del y s of x y at y equal to, sorry, not d dt, d dx, d dx, ax is nothing but this is at x y equal to x, then everything is at x equal to x star, right. There are two variables, but this variable is also depending on x. That means I have to apply the chain rule and do two derivatives, once with respect to this variable, second with respect to this variable. So, the first one is going to give you del del x del y, and this is s of x of y at y equal to x and x is equal to x star. We just write it at one shot. The second one is derivative with respect to y, but y is equal to x. So, hence it is trivially dy square s x y at y equal to x star. Okay, this is just the chain rule which we have applied. Right. When you do del del x, del del y, there will be another term dy dx, but I know y is equal to x, so dy dx equal to 1. So, that is gone from the chain rule essentially. Notationally, I am going to write this for convenience as s 1 2 star, 1 because derivative with respect to x, 2 because derivative with respect to y, and star because you are calculating everything at the evolutionary singularity. This one in this notation then is going to be a star and y twice, so 2 2, and this has to be less than 0 for CS. So, this less than 0 is the condition that your evolutionary singularity is a CS. Let us keep that in mind. This fine? What we are going to see now is you can have evolutionary stability, but that does not mean convergent stability, which is sort of not going well with the theorem which we had, that ESS has to be evolutionary, asymptotically stable fixed point, because that theorem was anyway for replicator equation. Okay. Now, when you are at the fixed point, this fixed point equation in terms of the, this is sometimes also called directional derivative. Okay, because you are taking derivative in a particular direction. So, this directional derivative which you have taken, in terms of that, this is going to be x y at y equal to x star. That is the condition of fixed point, because that is what it is. I have just rewritten it in terms of this, nothing, just by definition. That is where the fixed. Okay. But if this is the fixed point and at fixed point this is happening, it's already telling you that from the perspective of mutant in the adaptive fitness landscape, the fixed point is either a minimum or maximum, right. If the fixed point is maximum, then it conforms with the concept of evolutionary stability, because that is where it is the maximum, you would like to go there, anything. So, you want to know the condition when your fixed point is going to be maximum at the point x star. This is your function, maximum with respect to y. So, how do you write down the condition for one variable? If f(x) is a quantity where x is either maximum or minimum, then how do you find out whether it is a maximum or minimum? You calculate the second derivative, and second derivative should be less than 0, and that will give you maximum. So, let us write down that x star is evolutionarily stable. So, this evolutionary singularity is evolutionarily stable if del x del y, I have to take another derivative with respect to y, this at x star, I am not putting all those things anymore, it makes sense anyway, is less than 0. In the notation I introduced, it will be written as S22 star less than 0. Agreed? You can straight away see these two are not same, and one need not imply the other. Hence, evolutionary stability need not mean that in adaptive dynamics you are going to converge to the evolutionary singularity. Okay. But that does not say that evolutionary singularity is not, sorry, ESS or ES is not a fixed point. ES is still a fixed point, but it is something, if you are there, you may not be there, you can move away from there. Such configurations are in literature sometimes called Garden of Eden configuration, because they are so happy state to be in, but they do not exist. Okay. If something is both CS and ES, that evolutionary singularity has a name, it is called continuously stable strategy. These are just jargons after jargons, and there is no point memorizing them. For our purpose, as I said, what we want is, I want to understand that can I have a situation where speciation can happen. Specifically, I am after kind of speciation where from the ancestor another branch came out and both them of sort of there. Okay. So, if all this is okay, let us set it up, and in 10 minutes we can break up for coffee. See, it is very easy. This is one of the very nice applications of nonlinear dynamics. You just use the concept of fixed point and all and come up with some ideas. Okay. So, what we are going to do now is, we consider a situation where x star is CS, but not ES, very particular case. So, we have x star and I consider two nearby points x1 and x2 very near to x star, and I am interested in the quantity this. What I am after is I want to show that for such a configuration x2 can invade x1 and x1 can invade x2. How would I show that? Just by showing that x1 x2 is greater than 0 and s2 x1 is also greater than 0. If both happen simultaneously, then one can invade the other, right. The strategy is clear. I want to show that this has a possibility of invading this and this has a possibility of invading this. As per our desiderata or the assumptions we had, invasion implies substitution. So, hence the invasion exponent of this in the environment of this, if this is more than 0, then this would invade this, and similarly this will invade this, and they will substitute each other. So, I want to show this is greater than 0, and if I interchange the arguments, they can still will be greater than 0. It is very easy. So, S is equal to S1, this is x 1 plus x 2 minus x 1, I can write it like that. X 2 and x 1 are very close to x star. So, x 2 minus x 1 is a small quantity. I can now do a Taylor expansion, and that gives me S x 1 plus x 2 minus x 1 first derivative of S x 1 x 2 at x 2 equal to x 1 plus x 2 minus x 1 whole square by 2 factorial del 2 del x 2 S x 1 x 2 x 2 equal to x 1, and then higher order terms, which I always call terms too hot to handle. Fine, Taylor expansion, and I just expanded assuming S is a continuously differentiable function. Here I require at least twice differentiable. So, now let us argue that this is going to be greater than 0. Okay. What do I know? I know that x star is a CS. So, A of x star is equal to 0 definitely, because by definition x star is evolutionary singularity. Since it is CS, so dA dx at x star has to be less than 0, because it has to be stable, that is what we wrote there. This means if I come on this line and I am basically saying that here the value is 0 of A, but the value of A as x increases decreases. That means So, this implies, both of this together imply that A of x2 must be less than 0, because the value of A is 0 here, value of A is decreasing, and hence at this point it has to be less than 0. Let us look at this quantity. This quantity is del, okay, this quantity, if you look at it in the notation of A, what is this quantity? Just think about, just re-tag x2 by y and x1 by x. So, this is nothing but ax2, ax1, just by definition. Right. So, this is less than 0, but this is not what I wanted. I wanted what happens with x1, which will be greater than 0. If this is 0, then this has to be less, more, this has to be less. So, this is what I want actually. This I will require in the latter step. So, that means this is greater than 0. This by definition is greater than 0, by construction is greater than 0. So, this quantity is greater than 0. Agreed? This is 0 because we are at the demographic attractor. Usually, when I do linear stability and nonlinear all this analysis, I would stop here, not go to higher order terms by saying, you know, I am in such a small neighborhood that I can only work with the first order term, the other terms will sort of not contribute much, I can get rid of it. Here the problem is, this term can be arbitrarily small, because this term at x star is 0, because this term is nothing but this. I am in the arbitrary neighborhood of a 0 quantity, it is a continuous function. So, this can also be arbitrarily small, hence I should go to one step more at least to make sure that this remains, you know, greater than 0. What is this? This is nothing but the condition of ES left hand side, but I assume this is not ES, hence this has to be greater than 0. So, this is anyway positive definite. So, this is greater than 0, this is greater than 0, higher order terms I ignore, this is 0. So, this is greater than 0, as simple as that. Second part, because this is nothing but, this expression is nothing but this left hand side is the same thing. Just think x2 as y, it's retagging. Yes. Because I consider it not yes from the premise of my what I want to prove. Fine? Okay. So, I will do just in 2 minutes the other side and you can see it as well. So, now suppose I was interested in, maybe I should write it down. Let me write it here, you can compare then. So, if I were after same argument, so it is just now one liner. So, if I had this, then what should I, how should I expand it? x2 plus x1 minus x2, basically x1 and x2 will get flipped, that is all. So, I can write down that expression again with them flipped, x2 x1, x1 equal to x2 plus x1 minus x2 by 2 factorial square del 2x del x1 x2 x1 x1 equal, sorry, is that right? Yes, x1 equal to x2. Well, this remains, hotness does not go away, that is what you have, right. Now, the argument, now note what is this? This is ax2, ax2 is less than 0, this is less than 0. So, less than 0 times less than 0, greater than 0. So, this is greater than 0 again, this is anyway greater than 0. So, again this is greater than 0. So, both x(s1), x2 and s(2), x1 can be greater than 0 if x1 and x2 lie about a evolutionary singularity which is CS but not ES. We have configured a situation where this can happen. Okay. So, this would be a good point to stop. So, if you have any questions, you can ask.
So both of them are bigger than 0, that means
One can take over the other. If I had a population of x1, if I had a trait x1, if I had trait x1 and then x2 arrives, it can overtake, it can substitute x1. If I had trait x2 and somehow x2 was the mutant, x1 was the mutant, then it will substitute x2. They can substitute each other. And why is this happening? Because your fitness landscape is adaptive. When x1 comes, it sees a different fitness landscape. When x2 comes, it sees a different fitness landscape because the residents are different, and hence the possibility arises. If the fitness landscape was not dependent on the resident population, then it wouldn't have happened. So, it is a dynamic thing which is going on, and basically the game which is being played, the payoffs etc. sort of are conspiring in that fashion. But you have to have a very nice point where this happens. Okay, I mean sort of you have a point which is CS but not ES, only then this is appearing. Yeah.
will it like oscillate?
No, that is not the question. No? Whether it oscillate, you see, whether it will oscillate or not oscillate will depend on whether the mutant has come or not come. In my assumption of rare mutation and small mutation, mutant can come on this side, that side, whichever side, I do not know. Okay, it is not going to oscillate. What is going to happen is we will see, it is either going to move away like this or this is going to move away like this. Okay. But it has the possibility of substituting if this has appeared. Remember, this is a continuous space. That means a mutant here is more probable than this mutant. Okay. But this can come as close as possible, and then you can at least argue that there is a possibility of such coexistence. This is not telling you much, it is only telling you there is a possibility that I can have such a situation, that is all.
So, I still have some confusion about the original graph Sxy versus y.
Yes.
So, in that you are saying like given the value of y, what is the
At a fixed x, given the value of y, what is the value of x?
at a fixed time?
Of course.
Okay. So,
And as it changes, the graph changes. So your maxima can become minima, minimum can become maximum.
so okay, so if x is fixed, then what do you mean by saying ki, like what is y at this step becomes x at the next step?
Because y is, you understand what y is a trait. At that point, forget about maths. I am a mutant of a particular trait in a population. I am a black guy in a population of white guys, let's say, right? And then suddenly they all become black. So now x has become y. That's all I am saying. So now what I want to do is just show that within this formalism, I mean that part is actually quite involved. So sort of we make things very simple to just have a flavor of how this is done. And what is done? We want to look at something called branching point, which in our setting is going to lead to dimorphism, which could be taken as a mechanism of sympatric speciation. Where this branching point is a particular type of evolutionary singularity. These are just bunch of jargons. So, to make sense of the jargons, what we are saying is I have a population of traits, and since the population had only one trait to begin with, my population was monomorphic or you know, and now somehow there can be such evolutionary singularity that about that the two traits can come up. Then my population have two traits together. I would say my population is now dimorphic. In general, it could become polymorphic and all that. And if that happens, we are sort of saying theoretically, it is like some sort of speciation that has happened. Now, of course, formation of the species would require not only creation of the traits, but then creation of some kind of geographical or some kind of barrier which does not make them reproductively interact anymore, so that they lose the ability to produce fertile kids on mating after some time. Those are ad hoc things which have to be brought in later. But right now the first step we understand is that in a monomorphic population somehow two traits have to come up.
I had a question.
Yeah.
Like, one of our assumptions was it will always replace, like it will substitute.
Yes. Yes.
Mutant gene. Then
Yes.
how can two species like?
So that's what we are sort of going to discuss. Now you see, again, how can that come and not come? We are going to do it from the framework of maths. Okay, what it means, whether my mathematical framework is going to take care of it. We have to ask the question precisely so that I can get a valid answer for it. Okay, so right now I am here, for example, I am interested in the mathematical framework, and there we have to sort of work it out. So let us go through it, and then after that we can again come back to these questions. This sort of said it is possible that, you see, because this sort of said that if x1 can replace x2 and x2 can replace x1, it is possible that both of them can be there. That is all. It is an intuitive feeling that got generated. I would not go beyond that at this point. Okay. So, such a point where that branching can happen is called a branch point, which leads to dimorphism, which could be a mechanism of sympatric speciation. How to ask this question mathematically, is that what I am asking now? Okay. To be very frank, this is a topic which I had tried to read many times, could not understand in great detail because of all these derivatives and all that. So, this is for the first time I am presenting this. So, there might be something here and there, you have to just do not go by whatever I am saying, it might be wrong at some point. But I am trying to create the simplest setting through which maybe the concept can be understood. That is all my target is here. Okay. So, now I want to create a setting, and this branching point is essentially going to be CS, but not ES. I am going to take that as the definition. Usually it could be that you have ES and also CS, even then you can get dimorphism, but those are called converging dimorphisms. Population ultimately comes back to X star, but in this specific case you get what is known as diverging dimorphism, where the population will actually separate out. I want to see it in mathematical terms. Okay, I am not jumping ahead of myself, I do not know much more than that. I have written down some note, Sitabro will probably upload it, you can have a look. So, whatever is there. So, I am formulating this question in this fashion, that now suppose my population has two traits, x1 and x2. Then for both the traits I have to write down an equation, adaptive equation. The adaptive equation now should be a 2D equation, because I have coexistence of both the traits. This will be a function S which depends on x1, x2 both, because resident is now dimorphic, mutant comes in, the way the mutant is going to drive itself will be in the direction of larger and larger fitness, I mean the rate at which the fitness is highest, and of course this could be a different invasion coefficient, and similarly so my equation should be generalized like this. Here there is a catch, Now, there should be k in both of these, they might be different k's. If they are different k's, you can absorb only one k in time, the other k will float, and hence you may have k dependence coming up and all that. We are assuming that the mutations are independent of traits present, and hence k's are all same. So, I do not care about k's and all that. Okay. So, make it as simple as we can. Now, in this setup, if I were to show that population is going to diverge out x 1 and x 2, what is the mathematical question that I have to ask in terms of nonlinear dynamics? You see, this equation is going to have many fixed points, that depends on form of this. This form can be complicated, polynomial, transcendental, whatever, I do not care, it could be a very complicated form. Whichever points x 1 star and x 2 star pairs are such that both right, if this is 0 for both of a's, then this is a fixed point. How many such fixed points can be there? Many fixed points can be there, I have no clue. But my question is not about all the fixed points. My question is, I am looking for a fixed point which is x star, a very particular fixed point. And if I want to show that branching is happening, then basically I have to show that this fixed point is unstable. Then it means if I am in its neighborhood, x 1 and x 2 are going to separate out. So, I have made my question as a mathematically precise statement of what I want. How this came, what this came, I do not know. Okay. Now, if this is the fixed point I am sort of talking about, out of all the fixed points which I have to find out, if this is the fixed point I am talking about, then essentially I have to deal with functions like S1, x, x2, let us look at this. Okay, forget about what I said, just look at this. If suppose x1 and x2 are same, then basically writing x and x essentially means this is x only. It is just a tag for saying that I have two different traits, but they are same. It essentially means I can write it just like Sxy, right? Because it is just a notation. So, that means if I am after a fixed point like this, essentially a I x star, whatever is the fixed point, that should also correspond to your original A of the 1D equation as well. They should correspond to each other, because both of them being same essentially means you have a single population. Within the single population, you had made two populations out of them. So, finding the two components of this is equivalent to just finding one component of the 1D adaptive dynamic equation. So, the fixed point which we are talking about on that side of the board is essentially what is present there in both the coordinates of AI. Okay. So, that means finding this fixed point is easy, because somehow I have started with the construction, I know that fixed point there. Because my question was, in the 1D adaptive dynamics, if I know the fixed point, something happens about it. I want to show that that fixed point is unstable in the dimorphic formalism as well, and hence things are going to separate out. Okay. So, that is sort of the setup. Now, it is a very simple linear stability analysis of this equation, nothing more than that. It is a now 2D autonomous dynamical flow. This is a function of x1, x2, this function of x1, x2, that is it. And I have decided on which fixed point to work with, and I have to show fixed point stability. It is a little bit more difficult than first order ODE. Okay. So, let us do the linear stability. How do you do linear stability? You have to find the Jacobian. What is the Jacobian? Del A x1, del A1 x2, del A2 x1 and del A2 x2. This is the Jacobian. You have to find every term step by step. Let me do one term for you, other terms you can sort of plug it in. It is all about working with partial derivatives, that is all. So, let us work with the term del A1 del x1. This is nothing but del x1, A1 is nothing but this. So, that is del S1 del y x1 x2 y at y equal to x1, and this Jacobian has to be calculated at x1 star x2 star, right. You have to calculate Jacobian at the fixed point. So, this entire thing is being calculated at x1 equal to x star, y x2 equal to x star. Okay. There is something wrong, x1. Now, you have, we are not explicitly writing because it is going to become cumbersome. You have to keep in mind when you are taking partial derivative, which ones are kept constant, which one not are kept constant. When I am taking partial derivative with respect to x1, what I am keeping constant is only x2. Earlier there when we did those things, we had d dx, remember. So, now it is not d dx because I have x1 x2. So, that is where it becomes a bit messy, that is all. So, that means I have to do two derivatives, because this has been kept constant, I do not touch this, but I have to take derivative with respect to this and derivative with respect to y, because y depends on x1. So, this becomes del del x1 del xy square x1 x1 x2 y at y equal to x1 equal to x star, x2 equal to x star, and then there is a derivative with respect to y. Y is anyway equal to x1, so I can simply take the square x1 x2 y, and this is at y equal to x1 equal to x star and x2 equal to x star. Since at the end of the day I am going to put x star here x star and here x star, so ultimately I am going to the function S1 I do not have to write. So, this if you look at it is nothing but derivative with respect to the residents, derivative with respect to mutant, and I do not have to work with S1. At the end of the day this will become S. So, this in our early notation there is nothing but S star 1 2, and that in our notation is x star 2 2, right. What about the second derivative? It is only with respect to x2. And then you have y and you are taking derivative x2. So, because x1 y is fixed, so the second one is simply going to be S1 2 star. Okay. So, these things you can fill in, we do not have much time. So, just like this you have to do, and you have to end up finding. So, this is going to be S1 2 star plus S2 2 star. I have given notes to Shitabro, he will upload it, but you have to do these steps. So, this is S1 2 star, and this we have found out as S1 2 star plus S2 2 star. Okay. So, I have done one for you, others follow similarly, it is just boring algebra. Now, I know all the elements. Oh, I rubbed it off, fine, I had no choice. Boards do not have long memory.
So, could you explain what are S1, x1, x2, y in words?
In words, I have population with two traits present. One trait is x1, other trait is x2. mutant comes, that is y, that is it.
Okay, like growth rate when
S is the growth rate
of y
in presence of x1, x2. Okay. So, for simplicity of doing algebra, let us call this A, B, call it A, we can recognize this is also A and this is A plus B, right. So, what I have simply is, let us quickly do it, A plus B, A plus B. I want to find out eigenvalues to find out stability, I want to find out maybe eigenvector to see in which direction stability is, all that. Let us not go even up to eigenvectors, just find out eigenvalues. So, what are the eigenvalues? A plus B minus lambda whole square minus A square equal to 0, that is the characteristic equation. So, lambda is equal to plus minus A and plus A plus B. So, that gives me 2A plus B and B. So, two solutions of lambda possible, great. I am working in the premise where this is not ES, agreed. If it is not ES, then what is sign of B? B is S22 star, it is positive. So, 1 lambda is positive, which tells me that this x star definitely has to be unstable. Let us go one step more just to get more physical insight, because I have time. Let us find out the eigenvector corresponding to this. So, what is the eigenvector corresponding to B? What should I do? A plus B times A and A plus B, let the eigenvector be u v. I want to find in corresponding to this, I want to solve this to find eigenvector. So, this gives me A u plus B v plus A v equal to B u, and that tells me, what did I do? Not this. Why did I? There is something, A u plus B u, that is the thing. So, this cancels. So, this gives me u equal to minus v. The other equation is also going to give you u equal to minus v just by symmetry. So, that means my eigenvector is, the eigenvector corresponding to this is 1 minus 1. You want to normalize by 1 by root 2 if you want, but I know the direction. So, how does it look like in the phase space? What is the phase space? x1, x2, that is your phase space. You found one eigenvector which is this one, 1 minus 1. This is the eigendirection, this is the unstable eigendirection. You got the other one, if you do, it is going to give you 1 1, and it corresponds to A plus 2A plus B, this corresponds to B. Okay. And what you have found out, that this one is stable. Why is this stable? Because it is CS and not ES. So, 2A plus B will be less than 0. We can show that. So, 2A plus B means what? It is not necessary. No, it will not, because I vaguely remember that the the these two are the eigenvectors, and this sort of I think S12 or something, S11 probably, and then the signs. Okay. I mean, it depends. It actually will depend on whether this is stable or unstable. So, for the timing, let us not worry about this, whether it is stable or unstable. For my purpose, right now, this is going to work, that this is unstable. Now, if I take two populations, I make my population dimorphic in a fashion that they are symmetrically placed about x star, then basically I am saying I am on a point like this. Why? Because I am about 0. If I am about 0, one of the population has to be negative, one of the population has to be positive. So, that means I should be in this quadrant. So, I am in this quadrant. So, I am, this is my x star and this is my x1 and x2, and in this quadrant on this eigen direction, let us say, then essentially you are saying I am going to flow away, which means x1 is going to become more on this side and x2 is going to go more on that side. So, the population is going to diverge out, branch out, and hence one says this could be beginning of speciation, because at least population is not going to collapse back onto x star. Okay. So, within this formalism, this is how you can sort of explain how diverging dimorphism is happening. Okay. Now, this can be made more rigorous and all that. I am doing some very special cases, but the maths becomes very sort of messy because of all the partial derivatives. But the idea is just as simple as this, there is nothing more here. Okay. So, this is sort of it. So, what we have concluded in just 2 minutes, we have understood that what evolutionary game theory is a very sort of an umbrella language for understanding strategic interactions in evolutionary setting. Wherever there is strategic interaction, I need a language to do maths. Evolutionary games is a very natural language. You could get to all this maybe without even talking about evolutionary games and all, maybe somehow in a different way. Okay. I mean, this is not a new thing. I mean, people talking, I mean, if you go to genetics guy, they will be doing it in some other fashion, okay, trying to come to same conclusions and all that. But if you take this as a nice language, this sort of helps you in understanding strategic interaction, because the way to incorporate strategic interaction is only through games. And in evolutionary setting, games come easily. What we have found out that just like in classical games, concepts of equilibria are very important, and you have to have the right notion of what equilibria to work with. But equilibria are just static concepts. I need to incorporate dynamics to know how to go to equilibria. Depending on your dynamics, your equilibria can respond to your intuition in certain way. For example, when we had the replicator dynamics, your concept of ESS would conform to the fact that you ultimately go there. Okay. Here that may not happen, and all these things sort of we have done only for 2-player games and all those things, very in very simple setting. We have not even talked about what happens if you do not have fixed point equilibria. What happens if you have oscillatory equilibria? Because in nonlinear dynamics you get limit cycle, you get chaos. If you get limit cycle, you have a limit cycle attractor, you have chaotic attractor. If I ask you the reverse question, what is the game theoretic concept that corresponds to such equilibria? There is no consensus in the community that what would a limit cycle mean in game theoretic sense, what would chaos mean in game theoretic sense. In fact, it is so deeply deep rooted. One of the very sort of famous guy and authors in evolutionary games, Kreshman, in his text he explicitly writes, we are going to stick to simple differential equations, because if I take some other equations, I am going to get chaos and all those things, and usually in nature we do not see those things, so let us not go there. There is a sort of school which thinks that whatever random things you are seeing in the nature is you are seeing because they are transients. Ultimately they will settle down somewhere. But we know in various cases you get oscillatory solutions, all that. So what is the reverse thing? That I think sort of is an open problem, and that is where you can take all these dynamics and sort of do all that. Okay. So, with that I will sort of stop here. Supratim's time probably he should start, and we can talk over it, I mean over lunch or tea or whenever you want. Okay. Thanks.